Welcome back to Module 18 of Engineering Vibrations 1, an Introduction to Single Degree of Freedom Systems. In today's module, we're going to look at two learning outcomes. First, we're going to derive the differential equation now for a simple single degree of freedom system undergoing rotational motion. So far, we've only looked at translational motion. And for that system, we're going to find or solve for the natural frequency and the period of oscillation. So let's take this example or this real-world system that's undergoing rotational motion and see this demo. Okay, here's a demo of an actual real-world system, a pendulum. I have a sphere at the bottom, which I'm going to consider a point mass. I have a cord that's attached to that, and I'm going to say that cord's mass is negligible to the sphere. And if I pull it to the side here with some initial conditions, you can see that it oscillates back and forth. And so we have a natural frequency, radians per second, or we convert that to cycles per second. We also have a time that it takes to complete one complete cycle or a period of oscillation. So that would be start, finish, right? We got start, finish, and that's the period of oscillation. We can think of this real-world system as modeling, like a grandfather. I think of a grandfather clock, or maybe some ride at an amusement park where you get into this compartment and swing back and forth. So it is an actual system. So how do we develop the physical model for that system? Well, it's just a mass at the end of a string. And we're going to say that the string's mass is negligible. And so my model just looks as simple as this. Then we have to choose the generalized coordinate to describe this system's motion. We've seen this earlier. Q1 is equal to theta. That completely describes the motion of the system. So what should we do next? And what you should have said to yourself is, let's draw that free body diagram equals kinetic diagram. Here's the free body diagram. The forces that are acting on that are the weight of the what I'm going to call a point mass at the end. I'll treat that spherical ball as a point mass. And at the top, we have effectively a pin reaction. It doesn't prevent rotation, so there's no moment reaction. There's just reactions in the X and Y direction. And here is my kinetic diagram for that mass. As it goes in a rotational direction, we're going to have mass times acceleration. And that's equal to ml theta double dot. And you can review this in my earlier course, Dynamics, where I actually derived this. It's Engineering Systems in Motion, Particles and Bodies in Two-Dimensional Motion. And that was actually a prerequisite for this course. But as a quick review, if you recall, as something undergoes circular motion, we can call this the arc length, and the arc length, S, equals r theta. You should remember that mathematical expression. And r, in this case, the radius is actually L. And then we can take the derivative of that, which will be the velocity, and that equals L, because L is constant, theta dot. And then we can take the derivative again, and we get what's called the tangential acceleration, which is L theta double dot. And that's what you see here. In addition to the MA tangential kinetic vector, we also have an MA normal or radial vector. Again, you can review that in my previous course. It's M acceleration normal, or ML theta dot squared. There is no rotational kinetic vector because we're treating this as a point mass. The question becomes, why did we include the weight force on my diagram? We had talked about this before with the translational systems. Well, let's look at the static equilibrium position. In this case, all of the weight is being supported in the static equilibrium position by the reaction A sub y. So we can only omit the weight or gravity term when the spring force balances the weight in static equilibrium and throughout motion, as I said earlier in the course. And in this case, we don't even have a physical spring to balance out that weight. So here's my free body diagram equals kinetic diagram, and I'd like you to stop the video and ask yourself what you should do next. And what you want to do is your equations of equilibrium. We can sum forces in the y direction and the x direction on my free body diagram equals kinetic diagram, but the equation that's most important to us in this problem is summing moments. I chose to sum my moments about A. That way the AX and AY force reactions go through point A, and they're not going to tend to cause a rotation. You can see that the mg force is going to tend to cause a clockwise rotation. Counterclockwise is positive, and so that's negative. On the right-hand side, you've got your normal mass times acceleration normal force that's going through point A, so it doesn't tend to cause a rotation. We do have this mass times acceleration tangential that is going to tend to cause a rotation. So it is going to have a moment. Its moment arm is L. It's going to tend to cause a counterclockwise rotation. So this should actually be plus MA tangential times L. I said that it's going to undergo small vibrations, very small oscillations. And so for small oscillations, sine of theta can be estimated as theta. And we know that the acceleration tangential is equal to L theta double dot from the kinetic diagram. And so this is what I end up with. Again, let's put our plus in there for the right-hand side, as it should be plus. And this is our differential equation of motion. If I collect my terms, I have ml squared theta double dot plus mgl theta equals 0. We call the coefficient in front of the second derivative of the generalized coordinate m effective. It's really I effective, the mass moment of inertia effective, but I'm comparing it to our simple oscillator of mx double dot plus kx equals 0. So I'll often refer to it as just m effective. And the k equivalent is the coefficient in front of the displacement term, in this case mg over L. And we didn't have a physical spring. This is called a gravity spring. As the sphere rotated back and forth, the springing action came from gravity itself. And so, as I say, we call that the gravity spring. And so here we go again with our differential equation of motion. You'll recall our simple oscillator for translational motion. There was our differential equation of motion. There was our natural frequency. So m in this case corresponds to m effective. K is k equivalent. So I will be able to find the natural frequency and period of oscillation for this rotational system by just using the analogous terms. And so the natural frequency in this case, if I take the square root of k over m, masses cancel, L cancels with L squared, and I get the square root of G over L is my natural frequency. That's one of the answers we were looking for. And the period of oscillation is the time to complete one cycle. And that is 2 pi times the square root of L over G, as you see there. And that's our solution. As a summary, we derived the differential equation of motion for a simple single degree of freedom oscillator undergoing rotational motion, and we solved for the natural frequency and the period of oscillation. And that concludes this module.